Hi, my name is Afreen Bhumgara, and today I'm going to be talking about deep face recognition, a survey for EE432 statistical pattern recognition. So let's get into it. What is face recognition? Well, biometric recognition systems are ones where we have the automated verification and authentication of a person based on their biological, behavioral, or physiological characteristics. And face recognition is one such biometric recognition system. So earlier there were like other authentication based systems where there were like token based authentications or key based authentications, like password based authentication. So in token based systems, credit cards are an example of that, or password based systems or other authentication means. But passwords can be like breached, and token based systems, you can lose your credit card. So biometric systems have actually proved to be really helpful in the computer vision and pattern recognition community and in research in these areas. So face recognition is one such biometric recognition system, and it does is it matches human faces obtained from images or video frames against databases by measuring the facial features and mapping the geometry of the person's facial features. So it can be categorized into two sub-methods: face authentication or verification, and face recognition or identification. So in face authentication, it's a one-to-one method where you take a image query or an input image and you match it with another face template and you detect if both the images are of the same person. So the question that it answers here is this the person? And in face recognition identification, you take a one sample image and you match it against an entire database, and you find out like who is this person. So one-to-many approach is typically employed in government agencies or when used for law and enforcement. But one-to-one method is commonly used when you have to find them like in passport systems or for driver license systems where you have to check if two people are the same person. So applications of facial recognition are many, like the autofocus featured on our cameras, video surveillance, remote healthcare, cross-border security, expression recognition, the automatic indexing of images, and law enforcement. So it's a long-standing research topic in the computer vision and pattern recognition community. Like decades of research have been carried out on this field, and it's really interesting and exciting. So talking about face recognition versus other approaches, so as I said, biometrics like traditional approaches were token based and password based. But today, like we have a number of biometric techniques available. We have fingerprint recognition, voice recognition, iris recognition, palm recognition, even vein and body shape recognition. So it's really interesting how all these different techniques are there for authentication and identification. So the advantages, like why face recognition is such a prime like a prominent technique is because it's intuitive. It provides long range fully automated like identification. It has a secure and short processing time and really high accuracy rates. So when you take like your phone and you use your face ID, it's really fast, it's really accurate, it happens really quickly. So it's convenient, it's seamless, and there are no privacy risks because your biometric data is stored on your device. Like when you use face ID, it allows like exclusion of faces. So when it's used for public security measures or when it's used for like law enforcement, and it's contactless compared to other like measures in fingerprint recognition. You have to use your fingers, and even in iris recognition you have to be really like close. But in face recognition, it allows like contactless. So that's one of the strongest points of face recognition, and it's more resistant to cybersecurity attacks because like fingerprints can be spoofed and passwords and pins can be breached. So your facial data is unique. Um, so traditionally, like there are a lot of research, a lot of traditional research that has been conducted, and recently there has been a lot of deep learning research that has come into the picture for facial recognition. And deep learning approaches have become really, really famous. So we can categorize the two like separate approaches of how face recognition, the evolution of face recognition has taken place. So in traditional approaches, you usually use one or two layer representations. You use small data sets, generally where the size of the data set is less than 100. And you address like one aspect of unconstrained facial changes, like, the problems of illumination, affine transformations, or lighting, pose variations. And generally, you have unstable performance because you cannot extract features invariant to the real world changes. And eigenfaces, local binary pattern, and Fisher vectors are common traditional facial recognition approaches. In deep learning methods, you use multiple layers of representation and you have strong invariance to lighting, pose, and expression. And this has really reshaped the research landscape of facial recognition, because deep face, which is a deep learning technique, it actually achieved human performance for the first time by training a 9-layer model on 4 million facial images. So it achieved 97% accuracy. And actually, deep learning techniques have boosted the accuracy of face recognition by 99% in 3 years. So deep face recognition has two phases: the training phase and the testing phase. So in the training phase, the network learns feature representations of the faces, and it gets penalized by the loss function. So it rejects the false positives, and it particularly only selects the best matches in each iteration or each stage of training. And during testing phase, the model itself generates new features, and then you classify them with the results obtained in the training phase, and you figure out, how close are you. So this is how it goes on, and these are the two phases. So as I said, in the training phase, the network model is learning from large databases, and you generate feature vectors and templates for the test phases. But in the testing phase, again, there are like two sub methods: template learning, which KNN employs template learning, and subject specific learning. So model based classifications use that kind of approach. So talking about the major tasks of deep face recognition, you get an input image, then you do some pre-processing like face detection and face alignment, and then you perform the face recognition tasks, which are feature extraction, and then classifying the features, and then finally evaluating the accuracy. So this is the deep face recognition pipeline. And these are the major tasks of deep face recognition. So this is an example here. These are face detection results by the DCNN algorithm, which is a deep face recognition technique on 3 really famous face data sets. So a face cannot be recognized if it's not detected. So that's why detection must be robust, and the recognition process localizes the facial features or the face within the bounding box, as we saw in the previous image. And face tracking is used if the input is a video sequence. So there are two sub methods: feature-based methods and image-based methods. Feature-based methods focus on the local features. They are local methods, and they exploit geometric relationships among the facial features. They really pass when the filters match or they fail dramatically otherwise. And image-based methods, generally like convolution neural networks, employ this. They learn to automatically locate and extract the faces from entire images, and they have higher accuracy, but this is at the cost of computational complexity. Then the next step is deep face alignment, which is again a pre-processing technique. So here you see you give an input image, and different type of aligning techniques have been performed on it, like 2D alignment, data augmentation, multiple crops, and 3D augmentation. Um, and this is another example of these face alignments. So you can see the face is detected first using the bounding box in the first step. Then the facial landmarks are detected, and then we find we do 3D transformation. We find the frontal face view, and that happens with 3D augmentation. So this is how like deep face alignment helps us to find the frontal face image. And the first step, as I mentioned, was localizing the face within the bounding box. So alignment is not guaranteed because images are subject to like misalignments, to jitter and noise in real world. But with face alignment, we can detect like frames and faces, and we can normalize them to the canonical coordinates of frontal face views. And this is pre-processed to be consistent with the database. So this aims to generate the frontal view at different poses and angles. And the techniques that can be used to reduce the misalignments are landmark detection, data augmentation, pose estimation, and rendering. And some common approaches, as we saw in the previous image, were 2D alignment, multi-crops, 3D face specific augmentation, and scale rotation and translation augmentation. The next step is deep face extraction. So facial landmark detectors are used to, extract the features of the face. And there are three sub methods here: local methods, global methods, and hybrid methods that employ both. So local methods extract the local features like local binary patterns, SIFT use these, and they focus on only the key features of the face, like the eyes and the mouth, and they extract information about those features. Whereas globalized methods take in, like holistic methods, take the entire face image as the input, and ANN, CNN, neural networks, or histogram of gradient or bag of words use this. And hybrid methods combine the both the local methods and the global methods. So generally, what is used is that you first perform the first step, which is like localized features are considered using principal component analysis, and in the next step you use global techniques. But it's not necessary to actually combine both the approaches. You can use them together without integrating them. So initially, like when all the research into the face recognition period had begun, eigenvalues and eigenfeatures were used for higher accuracy. So they were combined, but they were not integrated. So integrating them is not necessary, but this is how it's generally done. And some popular deep face extraction algorithms are AlexNet, GoogleNet, etc. So in deep face classification, again, you have face identification and verification, and then a classifier is used to test the training samples and the testing samples and detect the best match. So comparison of faces is done with the test images in the database, and then using 1-to-1 methods or 1-to-n method, you find out the best match for the input face. So the sub methods are matching, similarity, and transformation. In matching, you find the best match for the face, and sparse representation based classifier uses this. In face similarity, you find faces most similar, and in face transformation, you generate new faces and you transform them. So the comparison of test face images and features with the training images is done here. And the accuracy is the summation of the successful attempts upon the summation of the recognizable attempts. So again, like deep face recognition methods can be classified into multi-stage methods, single-stage methods, and problem-oriented methods. So multi-stage methods like generate candidate bounding boxes and then have a number of iterations for rejecting the false positives and for refining the bounding boxes. So some algorithms that use these are cascaded CNN, faster RCNN, and faceness, and they have really high accuracy rates. So this is what happens at multi-stage methods. And single-stage methods, you accomplish the bounding box regressions and the face classifications in one step only. So this runs faster than multi-stage methods because obviously the number of steps are reduced here, but this happens at the cost of lower accuracy. So the other type of method is problem-oriented methods, where you deal with the problems in face detection, like rotation, blurriness, occlusion, and this is what we're going to focus on now, the problems of deep face recognition. So face recognition has a number of challenges because real-world images and real-world data is not uniform, and some common problems are pose variation, occlusion, low resolution, illumination, and facial expression. So here you can see that a person is there and he has like varying poses, and because of that, the location of the ROI changes, and you are unable to detect the ROI accurately. So pose variation methods here, because the complete structure of the face is not visible, the recognition is really difficult. They work on ROIs called ties, and they automatically enhance the entire digital image. So they aim to generate frontal face views with different poses. And the two steps are having the landmark facial detectors and then using pose and expression invariance techniques. So the algorithms are selected based on multiple factors, like whether training is required for the model, the computational complexity, if it's feature-based or appearance-based, and whether it's a single or multiple gallery image model. And some common approaches by researchers here, which have been employed for dealing with pose variation invariances, are the Weiler-Jones detector. It's really a very popular and widely known algorithm. The pose and expression normalization approach, energy range face. So these have been studied, and I have detailed more on them in the summary, in the survey. And here are the advantages and disadvantages of the approaches used. And as you can see that while some are simple, they don't need preprocessing, they're computationally fast, and they don't even have like training and facial component steps involved. But at the same time, they have disadvantages that they're sensitive to the pixel misalignments, or they can't handle when the variations are large, pose variations or edge distortions are caused. So it really depends the pros and the cons of each method, and using a combination of methods, hybrid methods, is what researchers generally do to achieve higher accuracy. So occlusion is the next challenge that is faced during facial detection. So occlusion occurs when your face gets blocked by a number of things like sunglasses or scarves, and the location of the region of interest is blocked, because of which we cannot detect the face accurately. So as you can see here, the faces are occluded. And The significant factors to consider when selecting the algorithm here are what features to use, the dimension of the feature space that needs to be sufficiently large, and we need to remove noise from images and signals. So some state-of-art approaches that have been proposed to deal with occlusion is a morphological graph model by Lee and a 3D face recognition system by Alus. So these are robust to occlusions, and they are able to handle, the non-occluded areas, able to extract them and detect the face in the image. So talking about how the methods are classified, they're classified again into local and global methods. So local methods extract local phase descriptors, and they only identify the occluded local regions, and they discard those local regions using the subspace methods. So they have a higher accuracy rate, and they reduce the feature dimensions with pre-processing. So SVM and local binary patterns use this, but then there's an additional step of occlusion detection, which adds some time. And in global methods, we don't detect the occlusion. We actually recover the clean faces from the occluded one. So we take the entire face as the input, and we reconstruct occlusion-free faces using linear combinations of images. So the advantage is complete restoration, but the limitation is a low accuracy rate, and it's sensitive again to the invariance one. So SRC and KNNPC and PCA use this approach. So we need to correlate the facial blocks which are occluded and the corrupted feature elements to achieve higher accuracy and handle the occlusion invariance. Here are some like common methods that they use, like, and what are the accuracy rates. So when the face is unobstructed, there is no occlusion. We have like really high accuracy rates, especially for deep learning techniques and hybrid methods. But as the occlusion occurs, and there is 50% occlusion, we even go down up to 55% from 90% accuracy. So that is how the challenge occurs in the face detection. Now, talking about low resolution, we have low resolution images that occur from surveillance videos of forensics. So the pixels are broken, and because of this, the image details are lost. So generally, the pixels need to be large and they need to be high resolution. So we can apply the high resolution techniques of feature extraction and detect the face. But because of that, because the image is low resolution, we first need to apply some techniques to make it and improve the degradation processes. So general like degradation processes that occur are blurriness, then large camera standoff distance, low spatial resolution, low compression settings, and noise that gets added to images, especially when illumination levels are low or due to overexposure or underexposures. So this is another image where we have like an example where we have a low resolution image, and we apply downsampling and super resolution techniques, and we resize the image and get a high resolution one. So some sub-methods to increase the low resolution faces so that high resolution techniques can be applied are super resolution methods, deep blurring, and hybrid methods. So super resolution methods turn the LR images into better quality images. GAN and CNN uses this. And deep blurring methods remove the blur from appearances using blind image deconvolution. So wavelets and point spread functions employ this, and hybrid methods combine both. They use feature vector distance matches. There are like some approaches stated by a number of researchers, like Yang stated the joint dictionary training method. Then Zhu used linear regression with two elements, new data and constraints. So hybrid methods combine both the local methods and the global method techniques. So however, all the low resolution research that has taken place has been done on low quality and constrained phase data sets. So better data sets need to be used so that we can achieve better accuracy rates. So the next challenge that is faced is illumination due to overexposure, underexposure, or due to shadows. You can see here that there is variance caused. And the steps here are first to pre-process the image to remove the adversarial effects of the illumination. Then you extract, like you have features of different scales and directions, and then you extract them. So the sub-methods are edge-based and image-based methods. Edge-based methods extract the invariant features like the edge, but they discount the shadows, whereas image-based methods retain information about the shadows because the object representations are closely tied to 2D images. So the advantage of edge-based methods is that it is really robust, and the limitation is that they are inaccurate when they occur, like when they face noise. So, but the current approaches that are being researched today, they still neglect the image quality and the I'm sorry, they pay attention to the image quality, but they neglect the recognition accuracy. So they even crop out the face area and sometimes the background. The next challenge is facial expressions. So as you can see here, there are different facial expressions at different levels of training, and they have been categorized into different labels. This is from a facial data set. And as you can see here, so again, like in facial expression recognition, there are three methods: pre-processing, learning, and classification. I've listed some methods here and the algorithms they used and whether the performance was good, what the speed was, and whether they were real time. So as we can see, like deep learning methods perform really well, but other methods like holistic and part-based methods are having like they lack somewhere. Either they're not real time or they have slow speed or performance. And here you can see that there's some misclassification that has occurred, like the label was discussed, but the model actually predicted anger. So this is an example of how facial expression difficulties occur. And here I've listed down all the state-of-art facial expression methods by different authors and the algorithms they used, like CNN or LSTM or neural networks, the data set they considered, the architecture, and what accuracy percent they obtained for each data set. So in terms of conclusion and future work, the accuracy of facial systems currently is lower than iris and fingerprint, and the existing database are not enough to train the deep networks. High intersubject variations and interclass variations exist because of the challenges of poses, elimination, unconstrained facial expressions, and identity bias. And the non-linearity coupled with the facial expressions require the deep networks to address the large intraclass variability and to learn effective expression specific representation. So what we need to tackle in the future is to have improved classifier training sets. We should handle data bias. We should handle occlusions, illuminations, and noisy labels. And we should aim to build lightweight, accurate models for face recognition and detection. So that's it from my end. I would like to thank Professor Yingwu to give us this opportunity to learn so much about the fields of computer vision and pattern recognition. I'm really happy to share my research, and there will be sure more of this detailed in the survey paper. Thank you so much.